So thanks to the organizers for inviting me to give this talk. It's called Skt Geometry. So the object of study of Skt Geometry is, Skt Structures. And of course, whenever I talk to any of my colleagues, what they ask is, what are those? So let me start telling you what Skt Structures are. Before I tell you what the S stands for, I'll just tell you what a Kt structure is. It's a Keller structure of torsion. It's just a Hermitian structure, so it's a metric and a complex structure together with a connection, and we require this connection to have a fully skew-symmetric torsion, and we require that it preserves the Hermitian structure, preserves the metric and the complex structure. This places no restriction on the Hermitian structure. Every Hermitian structure can be endowed with such a connection, and it's unique. It's known nowadays by the name of Bismuth Connection because of the work of Bismuth with this type of structure. Now, the strong, so the S stands for strong, and it's not really about the Keller structure being strong, but about the torsion being strong. So most likely it should be KST instead of SKT, but that's how it was named, and I'll keep the name. So a Keller structure with strong torsion just puts one extra condition on that three-form torsion, that we require that it's closed form. Well, I really can't make much sense of this kind of integrability condition when it's phrased like this. What does it mean in terms of the Hermitian structure for the torsion to be closed? But that's one way that it arises. You can rephrase everything in purely differential geometric terms, and it's just saying that you still have your Hermitian structure and you require the DDC of omega, so this is the Hermitian form that comes with the Hermitian structure, require that is 0. And if you want to know where H is in this picture, H is just given by DC of omega. So you can really phrase it either way, and this is what an Skt structure is, a Keller structure with strong torsion. Now, why would I want to start studying those? Good to have some examples, I imagine. So the first example we have, of course, are Keller manifolds. You pick H equals to 0 and everything becomes Keller.
Define DC?
Sorry?
Are you going to define DC?
I'm not going to define DC, but it's just the exterior derivative twisted by the complex structure. I was not planning to do that, but I imagine that maybe not everybody is familiar with it. DC is just minus del minus del. So you're in a complex manifold. Sorry?
Zero in the symplectic form.
If you have a Keller manifold, that's just 0 in the symplectic form. Sorry?
I hope you're going to define what you mean.
I'm a little lost here, so...
You're talking about a generalization of Keller, but obviously you're going to have to weaken conditions, but...
we are requiring that DC of omega is 0. The Keller condition is just the DC of omega 0, which is equivalent.
And H equals DC.
And then I'm just saying, if you check H equals to 0, so H is equal to DC in this context. Now if you put H equals to 0, if you force that, then you're back in the Keller case. So that's what's going on. So if you say, I would like to study some examples, one thing that you can do is say, I would like H to be 0, so that I'm saying that this connection with torsion is just a Levi-Civita connection, and you're just saying that you have a metric and a complex structure which are parallel for the Levi-Civita connection. That's a Keller structure. Okay? So, Keller manifolds are examples, and we can either see that from the closure of the symplectic form, plus integrability of the complex structure, or just in terms of complex structure which is parallel, a Hermitian structure is parallel for the Levi-Civita connection. Okay? Other bunch of examples are compact even-dimensional Lie groups. Any such Lie group has an Skt structure. Of course, none of them is Keller. Compact complex surfaces. So there is a result of Godeschon that says that whenever you give me a compact complex surface, you give me a metric on that one, compatible with the complex structure, and there is a unique representative of the conformal class of the metric for which the Hermitian structure is actually Skt. So you can always find any complex structure, you can just pick any metric compatible with it and you can rescale it to get an Skt structure. And that is in fact how people try to study, for example, the classification of complex surfaces. The starting point is always the fact that it has an Skt structure. You can actually also look at the moduli space of instantons over such a thing, and it again inherits an Skt structure from the underlying Skt structure on the surface. And you can even go a bit further, and instead of looking for instantons over surfaces, you could also look for instantons over just Hermitian manifolds with what we call Goldschmidt metrics. This one I'm not going to define, but it gives you more examples that are over bases which are more than just complex two-dimensional. Then this one, I don't know, some people don't like so much that, but well, let's say that you can study those in homogeneous spaces. A natural class of homogeneous spaces that one can study are, well, nil manifolds. They are easy to study. And up to dimension 7, we have a classification of all the nilpotently algebras, so you can actually achieve a classification of which, for example, 6 nil manifolds admit such a structure. Hello. So once we introduce this torsion term, what do we get? So let's just say here a few things that we know from Keller geometry. So Keller geometry, you have the composition of cohomology into the PQ components. So you have a complex structure, get PQ forms from the complex structure, and the cohomology decomposes according to those. That's often seen as a consequence of Hodge theory, which for me here mean identity of Laplacians. Of course, some people may say that Hodge theory may just mean, I don't know, the Laplacian preserves the decomposition and may not have to prove identity of Laplacian. So the term Hodge theory here is not precisely defined. You get that the Fröhlicher spectral sequence degenerates. Keller manifolds are formal. That's a consequence of this identity of Laplacians, or the DDC lemma. That's a result of the Lin, Griffiths, Morgan, and Sullivan. And Kodaira and Spencer prove that the deformation of Keller structures are also unobstructed, meaning that if you deform the complex structure, you can always deform the symplectic structure of it, so that the pair remains scalar. Now, I'll go back to those new manifolds example, because those were very concrete examples, so those were studied by Fino, Parton, and Salomon. So they're very concrete examples. You can just check these things. Do they still hold or not? Like, pick a few examples and see before you start trying to prove a theorem. So they really went for this deformation problem more than anything else in this list. But the fact that you say, well, these are complex manifolds, you still have a PQ decomposition of forms, and you can ask all these questions. And just by studying those few examples, they actually check that everything fails now. So in a way, this strong torsion is being stronger than what you'd like. And in fact, the closedness of age doesn't really seem to help you much here at all. So I'm coming to this whole setup from the generalized complex point of view. So for me, a Keller structure is a pair of generalized complex structures. One is a symplectic and the other one is a complex. So before I try to improve on this table, first I have to say something about generalized complex structures, in that this result of Kodaira, it says that if you deform the complex structure, you can deform the symplectic structure and they remain Keller. But the other way around is not true. So if you deform the symplectic structure, you actually get out of the Keller world in general. So from a generalized complex point of view, I should actually say that there are obstructions to deformations of Keller structures, so I actually make the table look a little worse. I'll put a yellow cross there. And the meaning of this yellow cross is that you need some further hypothesis, like the Calabi-Yau condition. That's the Tian-Todorov lemma. But without further conditions, let's say that it's not really true. Okay? So what I'll try to do is to improve this table. So the point of view of just looking at the composition of forms into PQ components from the complex structure, it misses an important thing, which is the torsion. It really disappears in this when asked these questions like this. So once you introduce the torsion, you have to find a new framework to look at these structures. And once you do that, you can actually turn this table into something a little nicer. So I actually proved today that the cohomology decomposes. You can develop Hodge theory. And there is a Fröhlicher spectral sequence that degenerates. I'll study the question of obstructions to deformations, and the point is that in Fino, Parton, Salomon, they look at this deformation problem, they just say, look, I have here an example. in this example, are the deformations obstructed or not? And they look, oh, look, they are obstructed. But there is no conceptual understanding of what's going on. What is the obstruction? Where do the obstruction classes lie? So I'll try to look into that as well if we have time. So just for comparison, we have a nearby structure that lies right in between Keller and strong KT, which is the generalized Keller structure in the sense of hitching that were studied by Gualtieri. And they also have a bunch of crosses and ticks. So the green ticks are consequence of Gualtieri work on Hodge Theory for generalized Keller structures. So all of those still hold. You have the generality of spectral sequences and everything. The question of formality, you need some further hypothesis which is similar to the one for the Tian-Todorov lemma. You need that your structure should be given by closed form. So you need something extra, but once your structure is given by closed form, you get that something is formal. And again, if the structure is given by closed form, the deformations are unobstructed, so that's a result of Goto. So I would like to, then the point is that generalized Keller is a pair of Skt structures, so it's really something that lies in between here. So the main insights to try to change that table to get those green ticks is that these Skt structures, they are not just what I defined earlier, which are purely differential geometric, but they actually fit more in what the audience of this conference likes to work with, I imagine. They are also generalized structures a la hitching. I use this straight from the NAF-SINET classification, but of course for this audience I might say that they are generalized structures a la hitching, Weinstein, Cervera, and a bunch of other people. But the point is that they actually live in current algebroids. They're not just something that you can define in differential geometric terms, but they live in current algebroids. There are some sort of complex structure there. And that is the correct framework to study them. Besides that, what we're going to do is actually step back from integrable generalized complex structures and integrable Hermitian structures and just say, what if they're not integrable? What's stopping them from being integrable? So I'd like to study the intrinsic torsion, the things that stop integrability from a generalized complex structure, generalized Hermitian structure. And once we have a description of those, we can also progress in the integrable case. So this is the outline of the talk. I'll start telling you about the geometry of T plus T star. Then I'll go into the Nine-House Tensor, so the lack of integrability of a generalized complex structure, and get intrinsic torsion out of it. And then I'll develop Hodge Theory for a bunch of things. And if everything works well, we still can do deformations in the end of the talk. Okay? Are we okay until now? Thank you. So the first thing that you have in T plus T star is just a natural pairing. So it's not just any bundle of your manifold, it's the sum of a bundle and its dual, so you can always evaluate the one on the other. So you have a symmetric pairing which just picks, so for me x's and y's are vectors, xi's and ethas are forms, and you can just evaluate the forms on the vectors. That's what it is, so it's a symmetric one. There of course is a skew-symmetric version of the same thing, but we have no use for that. At least I don't have any use for that. T plus T star acts on forms. You just can wedge with your form and you contract with the vector. And the nice thing of this is that it actually extends to an action of the whole Clifford algebra of T plus T star. So if you act twice with V, what you get is just the norm of V acting on phi. So that's precisely what defines the Clifford relation. So you actually get an action of the whole Clifford algebra, not just T plus T star. And that means, makes this space of forms on T star as the spinors for T plus T star. So we can actually, that from our point of view, that's the correct way of thinking of it. Technically they are spinors, so the even forms and the odd forms are spinors, but we just call them spinors. And being spinors, as they are, they get a spinning variant pairing, we call the Chevalier pairing. Everything here is a little twisted, so in principle the spinning variant pairing picks two spinors and gives you a complex number. For me, it gives me a top degree form, so my whole set of spinors has been twisted by a square root of the determinant bundle of my manifold. But this is a very simple thing. It's essentially the wedge product of forms. What you do is that if you have one form here, you want to know what is the pairing of those two forms, you flip one of them, you transpose it, you wedge them together, and you take the top degree form. So this is what you do to get this pairing here. And I'm not going to write it down, but it's essentially the wedge product. It changes signs depending on the degree of your form. So it's just pretty close to the wedge product of forms. So once you start, I'll start putting structures on T plus T star. The first geometric structure that I'll put here is the Generalized Metric that was studied already by Gualtieri and Witt back in their thesis in 2004, 2003. A generalized metric for me is just an orthogonal self-adjoint bundle isomorphism. So it's something that sends T plus T star to T plus T star in such that this thing here is positive definite. So orthogonality is just about asking that it is compatible with the pairing. The pairing is already there in T plus T star, so you cannot just ignore it. You should always require that things are compatible with the pairing. The self-adjoint property is just to say that this is a symmetric tensor. So if you pick this one at GVW, you should get something symmetric as a metric should be. Now here you have that it's orthogonal, so the inverse is equal to the transpose. It's self-adjoint, so the transpose is equal to G itself, and then you see that G is G inverse, so G squared is the identity. That means that G splits the space of splits T plus T star as a plus 1 and a minus 1 eigenspace, just because it's a matrix whose square is 1. So and it's determined by its plus 1 eigenspace. So this is the picture that we have here. So the vertical and the horizontal axes are T and T star, and now I'm getting a plus 1 eigenspace for G. This, of course, since G is just plus 1 here, it means that the natural pairing is just positive definite in this space. V minus is the other eigenspace, so since it's self-adjoint, this other eigenspace is orthogonal to the first one. And since G is just minus 1 here, that means the natural pairing is negative definite. So both of them have to have dimension n. The same dimension as the manifold itself. Okay. And of course, once you have V, since V minus has to be the orthogonal complement of V plus, then you're done. So V plus determines your metric. Now, once you have a metric, maybe the next thing you do is to put a Hodge star in it. So this is something that, this version comes from Gualtieri. Frederick Witt had something it's the same operator, maybe described in a little different way. So if you give me a metric and orientation, you can define a Hodge star. I'm not going to particularly write you how to define it, but the fact is that it gives you a positive pairing if you use the Chevalier pairing. So it's not really the usual Hodge star. The Chevalier pairing changed from the wedge product of forms by some signs depending on the degree you are at. So this is essentially the same thing. It changes from the usual Hodge star by some signs depending on the degree you are at. Okay, so it's essentially the usual Hodge star with some sign changes. One good thing that comes out of the sign changes is that now this new Hodge star squares to a single thing. So m here is the dimension of my manifold, and just squares to m minus 1 over 2. So it doesn't depend on the degree of the form anymore. So it's a little different from the usual Hodge star, which normally if you square in an even dimensional manifold, it's, depends if you're in an even or an odd form. So now it doesn't depend on that anymore. So you actually can just split the space of forms into self-duals and anti-self-duals, which are just the eigenspaces for this operator. Okay, so I'll just call self-dual forms the ones that are in the minus I to this whatever power here, eigenspace, and the anti-self-duals are the other ones. Of course, in some cases, depending on the value of m, it will be that star of alpha is actually equal to minus alpha for a self-dual form, which is a little odd. But I'd like to just have a single definition that works for all dimensions. And the signs here were arranged so that if I'm in a 4 manifold and I have a 2 form, then the concept of self-dual agrees with the usual concept of self-dual. So if I was going to study instantons over a 4 manifold, I don't have to be telling according to my self-dual or your self-dual. So there is some agreement, but in general you have to just look and see what's going on here. And it's something that works in every dimension. It's not just in 4-dimension or 4k dimensions, okay? Next thing that I'd like to put in T plus T star is at least an almost complex structure, so I don't have integrability yet. So an almost complex structure is just a bundle automorphism, again, which should be orthogonal with respect to the pairing, because the pairing is there and should always require things to be compatible with it. And you require that it's a complex structure, squares to minus 1. So that's all. It's really just a complex structure on T plus T star which is compatible with the pairing. It's fully determined by its plus I eigenspace, so this is L. properties of L are that it's a maximal isotropic subspace that comes just from the orthogonality of J. So it is actually one of these linear Dirac structures that we study here. And it has only one difference from the usual Dirac structures that we study, which is that L intersect L bar is empty. It has just the origin. So it's just a usual complex Dirac structure with one non-degeneracy condition. So just a small, apparently just a small extra thing that you ask there. Again, so J is orthogonal, so the transpose is equal to the inverse, but J is a complex structure, so the inverse is just minus J. So you see that J is equal to J transpose is equal to minus J, so it's a skew symmetric operator if you think of it that way. So it's actually something wedge 2 of T plus T star, and wedge 2 of T plus T star, if you have in mind that identification of the Clifford algebra, this is just the Lie algebra of the spinors. The algebra of the orthogonal transformations of T plus T star. So it acts on spinors. It's in the algebra of the spin group. It acts on spinors accordingly. So if you let J act on spinors, it actually gives you the composition of forms. So it's not the usual PQ decomposition that you have in a complex setting. It's a different one. In some cases you can actually relate the two of them, as we will do later. But the point is that this, from our point of view, this is the correct decomposition that you should consider in forms. And if you want to, as I want to get to later, decompose the cohomology of a manifold according to some decomposition of forms, it's very important to have the correct decomposition of forms to start with. Otherwise you can't prove anything. So that's one reason why they could not prove things for Skt structures earlier. That they were just looking at the the usual PQ decomposition, and that's not the correct one to be considered in this context. A generalized almost complex structure. So now you just have a metric, have a generalized complex structure, and you just put the two of them together. And of course, it's not just a matter of having a metric and a generalized complex structure. You would like these things to be compatible. So the compatibility condition is just asking that the corresponding automorphisms commute. That's all we require. So this would really be the case if you have an ordinary Hermitian structure. You can just pick the G to be the metric. A usual metric defines one of these curly G's here. You can pick J1 to be the generalized complex structure defined by the complex structure, and those two together give you a generalized almost Hermitian structure. So it's really a generalization of that concept of just usual Hermitian structure, but now it also is compatible with the idea that if you have a symplectic structure, you can pick a compatible metric, and that also gives you a generalized almost Hermitian structure. Whenever you have one generalized Hermitian structure, you can find a second generalized complex structure that's just the product of G and J1. So from the fact that they commute, G squares is plus 1, J1 squares is minus 1, so this whole thing here squares to minus 1 as well. So you get a second generalized complex structure for free. So there is no integrability here yet, right? So it's really analog to saying that if you have a complex structure and a metric, you get a Hermitian form, you get some sort of symplectic form. And if you have a Hermitian form and a metric compatible, it gives you a complex structure. So that's all that's going on here. Integrability is not really asked at this point yet. It's just the linear algebra of the situation. Now when you have this, you can start decomposing your space of, say, T plus T star in the space of forms into intersections of eigenspaces. So you have here a number of operators, G, J1 and J2, and they all commute. So you can start decomposing your all your spaces into intersection of eigenspaces instead of just eigenspaces for, say, J1 or G. So V plus we had there was the plus 1 eigenspace for the metric, and now we can actually decompose this plus 1 eigenspace into the plus I eigenspace for J1 and the minus I eigenspace for J1. Similarly, V minus can be decomposed into the plus I eigenspace for J1 and the minus I eigenspace for J1. So I'm just keeping track with usual convention in complex rule that you put 1, 0 to say these are the plus I guys, and the 0, 1 to say they are the minus I eigenspaces. Okay? Similarly, you can look at your space of forms, and each generalized complex structure individually gives you the composition of forms into these UK spaces, which were the eigenspaces for the Lie algebra action of J1. Now you have two, they commute, so you can decompose the space of forms into intersections. So you have here a new PQ decomposition. It's not quite the same one that you have. Even if they are just complex and symplectic, this is different from the usual PQ decomposition of forms that you get in a Keller that you normally associate to a Keller manifold. So you get the composition of forms, and I find it easier if you actually put it in a graph. So here this is a representation of the non-trivial spaces that you get if you have a 6-dimensional manifold with one of these generalized Hermitian structures. You get a bunch of, get everything in a diamond. So this spaces here at the corners, they're actually line bundles that determine my structures, and you can move around just by action of these V pluses and V minuses. So each one of these guys acts in a specific way, either going up or down, or so that you can actually relate the action to this decomposition here. Now, besides having these things, you also have the Hodge star, and one of the features that we have in Keller geometry is that the Hodge star is related to the complex in the symplectic structure, and yet that relation is somewhat messy. And by having this setup, this is something that Gil Cavalcanti noticed in his Hodge Theory paper, you get a much neater explanation and relation between the Hodge star and J1 and J2, the action of J1 and J2. It's just the exponential of the actions of J1 and J2. So if you are in UPQ, it's just I to the P plus Q. So it's a very simple action. If you think of what the Hodge-Hiemann bilinear relations tell you, they seem somewhat complicated. I don't know if who is familiar with those, but they seem somewhat complicated. And this is just some sort of artifact from the fact that you are looking at the wrong decomposition. So here now we have the Hodge star. It's very simple, and you see it depends only on P plus Q. So you can actually tell which ones are the eigenspaces of the Hodge star if you have the eigenspaces, this PQ decomposition here for J1 and J2. So if you go back to our picture we had before, you can color things in terms of self-duals and anti-self-duals. That's more or less how it goes. I hope you can see. Yes, that's okay. So the red ones, I hope you can see it's red. Can you see it's red? No? So let's call them black. The black ones are self-duals, and the green ones, I think you can see they are green. They are anti-self-duals, and they just alternate, because that's what happens with some P plus Q. They alternate in the diagonals. So if you want to know which ones are the self-duals, they are alternating the diagonal, and the signs are arranged so that the top diagonal on any dimension is always made of self-dual forms. Okay? So you can actually read all this information from this diamond. Now, to put integrability, until now I had no integrability whatsoever. To put integrability you need a bracket, and the bracket is the Courant bracket that we have been hearing until now. So I use the twisted Courant bracket. It's important to have this tree form here, and this is the expression for it. This expression is not very enlightening in general. Maybe a better way to think of it is that the Courant bracket is the derived bracket from the operator dh. So if you remove h, that's what Dorfman noticed, and that's why some people today like to call it the Courant-Dorfman bracket. And later on, once the twist came into the Courant bracket, you can just put h's everywhere, and that's the relation. So it's the derived bracket. I'm here thinking that sections of T plus T star act on form by the Clifford action, and this thing here in principle would just be another differential operator acting on the form phi. But in fact, it's not a differential operator at all. It's a tensor. It's just another section of T plus T star, and that's how you define the bracket. And you can just do a computation to get that this is the expression for it. Okay? So one thing that comes out of this equation is that if you are putting twisted Courant brackets, if you are looking at this bracket with h, you should not really consider the realm operator. You should not really consider d. The correct operator that's suited to deal with the twisted Courant bracket is dh. So if you start asking questions about d or del plus del bar and you forget about the torsion, you're bound to get bad answers. Okay, so if h is there, you should just include h in your question. And that's another reason why the table is full of red crosses on the side, because the h was just missing from those questions. So let's just say something about the Nine-House Tensor. So this is, you can just define it somewhat similar to the usual one. I have just done a little tweak. So if you give me three sections of L bar, so the minus eigenspace of J, you can take the bracket of two of them and pair with a third. And the idea is that normally you define the Nine-House Tensor should just be the L component of this bracket. You don't pair with a third thing. You just say that the Nine-House Tensor, you pick two guys in the minus I eigenbundle, you bracket them, and you take the 1,0 component. Now what we are doing here is that since L bar is maximal isotropic, you see that if this thing here vanishes, that means that this bracket is always back in L bar. So if this thing here vanishes, you get integrability, and actually it's equivalent to integrability. So J is integrable if and only if the Nine-House Tensor vanishes. Okay, and besides that, here I'm using a bracket, and bracket of course is some sort of differential operation to these things that I'm putting inside. But in fact, N itself, just as usual, is not really look at that, they come together. It's not really a differential operator, it just really is a tensor. That's why really it's the Nine-House Tensor, not the Nine-House operator. It is in wedge 3 of the dual of L bar, which I'm identifying with L by the natural pairing. Okay? And then this picture here, what I'm showing to you is just that if you give me a generalized almost complex structure, no integrability required, you have the UK decomposition of forms, and you apply DH to say a form in UK, and you see where does it land. And at first you might think it's a mess, it lands everywhere, but in fact it doesn't land everywhere, it only lands in 4 spots. And the spots are the adjacent ones, so you can increase the index by plus or minus 1, or you can increase the index by plus or minus 3. And the operation that increases the index by plus 3, for example, is just the Clifford action of this element here in L. Okay, so it's a very concrete way to go from this definition of the Nine-House Tensor that's somewhat standard, and something that maybe I find it a little easier to use on computations. And you also see here that if the Nine-House Tensor vanishes, so these 2 arrows here, this arrow here and this arrow here also vanish, and therefore D decomposes as del plus del bar, which is another standard way to express integrability of a complex structure. So you really see things filtering through. Now I'm interested in generalized Hermitian structures, so I have to have a pair of almost complex structures, generalized almost complex structures. And of course, now if I don't require any integrability, then DH can change either the P or the Q degree by plus or minus 1 and plus or minus 3. So you see that there should be 16 components. So you imagine it would be a very complicated diagram to draw. It wouldn't seem very enlightening, but you don't have to imagine that. Here it is. If you thought a spider had many legs, yeah, it could have more. So that's the diagram. These are all the components of the age. If you apply it to something in UPQ, the intersection of UP of J1 and UQ of J2, what you get is this 16-legged beast. And hopefully the idea is that by understanding these things, so here are the different components of the Nine-House Tensor. So these guys here tell you about integrability of J1, and these guys here tell you about J2. These guys here on the vertical part tell you about integrability of J1. So they're all together, they're all tensors, they're all parts of different Nine-House Tensors of J1 or J2. And they are what obstructs integrability. So hopefully you can tell something about the geometry by just looking at the vanishing of certain components. And of course the most obvious things you can do is say, well, if J1 is integrable, then the P degree cannot change by more than plus and minus 1, so the DH has only these 8 components here. Now it really became a spider. If J1 and J2 are integrable, then DH should have only 4 components. And therefore you have such a picture for a generalized Keller structure, which is a pair of integrable J1 and J2. So, and this is actually equivalent. So it's saying that DH decomposes like this is equivalent to the generalized Keller condition. So you see that from the vanishing of these components, you can say something about integrability of structure, and therefore it's natural to actually call them the different components of the intrinsic torsion, because that's what the intrinsic torsion does. It stops integrability, measures the lack of integrability. So if all of them vanish, you get a generalized Keller structure. If some of them vanish, you can say something about some sort of integrability of your structure, but maybe not necessarily all of it. It's not a generalized Keller, maybe it's something less. Now I can finally get to the Skt structures that I promised. And the point is that this is something that Gualtieri essentially noticed in his thesis. It's a lemma, it's a computation that he was not really worried about Skt structures there. It was something on the route towards the generalized Keller by Hermitian equivalence theorem. So I noticed and expressed it clearly in 2006. But the point is that you can express this Skt condition in terms of Courant bracket and integrability of some distribution. What you have now is that instead of having a generalized complex structure in the whole of T plus T star, you just have a generalized complex structure on V plus, so just on the plus 1 eigenspace of your metric, and you require that the plus 1 eigenspace of that complex structure is closed with respect to the bracket, so it's similar to a usual integrability condition again. And of course this I'm saying positive because I'm putting everything on V plus. I could have done everything V minus, and you have what we call a negative Skt structure. And one good thing of looking at this thing here is that it's phrased in terms of brackets. Now if you think of what the expression for the Nine-House Tensor was, you take the bracket of 2 things and pair with a third. Now if I'm in an Skt setup in which the bracket of 2 guys in V plus 1, 0 goes back to V plus 1, 0, that's automatically orthogonal to anything in V minus or V plus. So what I'm going to do here, just to be able to keep on using this kind of setup that we have here, if I'm given an Skt structure, I'll just pick, say, a positive one. I'll just pick a complex structure on the minus, on V minus. Any one will do for now. So it's a unnatural extension. You just pick one and can phrase everything back in terms of generalized Hermitian structures by using the complex structure on V plus and the complex structure on V minus and extending that by linearity. So because I have this expression here and it lands back always in this space, I can conclude the vanishing of some of the components of the Nine-House Tensor. So DH has this, well, still somewhat complicated looking expression, but it has less components. So this whole corner here is missing now because of this condition here. The integrability condition for an Skt structure forces the vanishing of this whole corner here for the Skt, for the generalized Hermitian structure. Similarly, you could have done the negative one, and there is some sort of symmetry here going on. If you do for a negative one, you just get this. So now the corner that vanishes is the downward one. Okay? And if you flip between these two things, so say you have an Skt structure on V plus and an negative Skt structure on V minus, you can actually flip back and forth and see which arrows actually remain. And the only arrows that remain between those two things are the 4 arrows in the middle. All the other arrows have to be 0 because it's a positive and a negative Skt structure, so you actually get to a generalized Keller structure. So this is a pictorial, a graphic proof of Gualtieri's theorem from his thesis, that if you have a pair of Skt structures, a positive and a negative, you actually have a generalized Keller structure. Okay. Now let's go back here to this setup. So of course I said that to make this diagram I had to make an arbitrary choice of a complex structure on V minus. So I could phrase everything in terms of the UPQs. These UPQs are not natural for the Skt structure. The things that are actually natural, they are the eigenspaces of I plus, they are the diagonals of this the composition. So each diagonal is the sum of the UPQ over P plus Q equals some constant is a well-defined space in terms of just Skt data. The rest of it depends on that choice that I made of complex structure on V minus. So when I look at this, I see the DH, even though it's looking very complicated, it's picking something here and it's only mapping either one up in the diagonal or one down in the diagonal or into the diagonal itself. So DH has only 3 components in terms of the natural decomposition of form. So that's what you get here. So my W's are just the sums over P plus Q equals to constant. So they are the diagonals of my decomposition. And generalized almost Hermitian structure is an Skt if and only if DH only maps either up or keep the diagonal or maps down the diagonal. So that's an equivalent description of an Skt structure. So this is about identifying the correct differential operators associated to an Skt structure. In the same way that Hui was making this point in the Poisson school, that you may want to treat Poisson manifolds with just exterior derivative, but if you start asking questions, the exterior derivative will not answer those questions. You need Poisson cohomology. So here what they're doing is actually identifying the correct operators that you should consider when you're looking at an Skt structure. You have delta plus n that maps up in the diagonal and its complex conjugate which maps down in the diagonal, and the WK which preserves the diagonal. So these are the natural operators you have if you have an Skt structure. Of course, what you can do, and now the picture starts to become much nicer, is that it's just possible to always not just extend arbitrarily some complex structure on V minus, but you can actually choose the complex structure on V minus. So that's the generalized complex structure corresponding to it, the J1 is integrable. So you lose all the arrows that were on the side here as well. So what's going on here is that if you remember, the Hermitian case had 2 components of the Nine-House Tensor. One was coming here and the other one was coming here. And now that component is gone. And the generalized Keller case doesn't have this component. So an Skt structure is actually halfway between generalized Hermitian and generalized Keller. In a very precise way. You have only, of all those spidery arrows that you had in the first diagram, you have only one component left of the intrinsic torsion for the Skt case. So it's actually seems to be as close to being very nice as you could ask without actually asking for it to be very nice. And you get a corresponding decomposition of cohomology. And actually, I would just like to go back to this. So here I mentioned delta plus n as the thing that goes up in the diagonal, and in this diagram here it becomes clear that it's just the sum of delta plus and n. That's why it's called delta plus n. So the sum of 2 operators, that's what goes up in the diagonal, and the delta minus slash is the sum of delta minus and delta minus bar, and so on. Okay, So now I think I'm in condition to do some Hodge theory for you. How long do I have? 15 minutes? 20 minutes, okay. So now I'm in condition to tell you something about Hodge theory of these manifolds. So first, even before you put Skt structures there, just have a metric, an orientation. You can start talking about operators, and the operators that I'll find interesting are not necessarily D or DH or DH star or the Laplacian. I have an intermediate operator, which are, well, these two, actually I have two intermediate operators. It's the sum of D plus D star with a sign in the middle, and the sign depends on the dimension. Okay, so it's essentially D plus D star. So it's some sort of a square root of the Laplacian. The good thing of these operators is that they're actually compatible with the decomposition of forms into self-dual and anti-self-dual. So D plus maps self-duals to anti-self-duals and vice versa, so it changes the duality of your forms, while D minus preserves the duality of your forms. Okay? And of course another nice thing that they have is that both of them square to the Laplacian, except for some constants. So if you want to find harmonic forms, you don't have to find a 0 for the Laplacian, you just have to find a 0 for D plus or a 0 for D minus. Okay? Now, the theorem here is that if you had a compact Skt manifold, the DH cohomology splits according to the decomposition to the diagonal. So WKs were the diagonals I had earlier. So in a compact Skt manifold, this is the composition of forms actually gives you the composition of cohomology as well. And this theorem is actually true also for parallel Hermitian structures with closed torsion. So this is, I'll just make a remark about this later. But let's just prove the theorem. It's a very intricate proof. Fasten your seatbelts. So this was the picture for DH for an Skt structure. It had all these different arrows, and I'm here not making any particular assumption of the complex structure I'm choosing on V minus. Any one will do, okay? Now I mentioned that the self-duals and anti-self-duals, they are the diagonals of this decomposition into UPQs. So you can color it. Again, you have, I imagine, black instead of red. Black and green. So the idea here is that I'm just singling out which ones are in the same duality and which ones are in the opposite duality. So if UPQ was a self-dual, then these guys here in this diagonal are all self-duals, and these ones in the nearby diagonals, they are anti-self-duals. Now if you think, again, what I just said about D minus is the part of DH which preserves the duality. So if you were to look at what D minus is, it's just that. So D minus preserves the diagonals. Therefore the Laplacian, which is the square of the D minus, also preserves the diagonals. So in particular, the kernel of the Laplacian gets split into this diagonal decomposition. Actually, all the eigenvalues, all the eigenspaces of the Laplacian get decomposed into this diagonal decomposition of forms. So it's something a bit stronger than just saying that the cohomology decomposes. It's just really that the Laplacian preserves these diagonals. Okay, so that's the proof. Now I also mentioned something about things which are parallel with torsion, so I didn't really say much about those. So the point is that even though we are here doing Lie groupoids and Poisson structures and so on, what happens is that this current bracket somehow is a magic tool. And if you're doing Riemannian geometry, you might also want to know about the current bracket because it knows about the Levi-Civita connection. And if you put this age current bracket, it knows about the connections with closed metric torsion plus and minus age. So this is something that Hitching noticed a few years ago, that you can actually phrase those connections just using the current bracket. I'm not going to go into that, but with that knowledge it's to be expected that you can rephrase the parallel condition in terms of things that I have been telling you, and indeed it's an even more complicated diagram. So if you just know that you have an almost complex structure and a metric which are parallel for the connection, say, torsion age. So this is just saying that that connection has holonomy in UN. Then these are the different components you get for your DH, and you see that D minus, so the one that actually preserves the parity, is still the same. So this picture here for D minus is the same whether or not you require that the complex structure is integrable. It's really something about reduced holonomy. So there you go again. D minus preserves the diagonals. The square of D minus is Laplacian preserves the diagonals, and therefore you get that the cohomology of any parallel UN structure also gets preserved, is decomposed into these diagonals. You could go a bit further and say, what if both of them, the connection torsion plus and the connection torsion minus H, have reduced holonomy? They both have holonomy UN. So of course this would be, a particular case would be the generalized Keller structure, but right now I don't require the complex structures to be integrable. You still get the same thing. So this is the theorem that's if you have parallel bi-Hermitian structures, then you actually get to the composition of forms into the UPQs now. And the proof is just the same. Now the parallel condition for one of them means that these two components of the Nine-House Tensor vanish, the intrinsic torsion vanish. For the other one you get that these two components vanish, and altogether you just get this nice X. So D minus is the same one, so you get that the Laplacian preserves the diagonal. D plus is the other part, and the square of D plus is the Laplacian, and also the Laplacian also preserves the anti-diagonal, so it preserves the intersections of those things. And you get that as long as you have reduced holonomy, you get the composition of the cohomology into UPQs. And well, reduced holonomy is not something about UN, so really I have been describing everything here in terms of generalized terms, I imagine, in terms of generalized Hermitian structures. But really something about reduced holonomy. I mean, this theorem doesn't require integrability of anything. So the actual theorem is this. If you have a compact Riemannian manifold, a closed free form, and metric connections with torsion plus and minus H which have reduced holonomy in G plus minus, so it can actually be two different groups. In the Skt case was UN cross SO2N. Then you get the corresponding Lie algebras. They sit inside wedge 2 of V plus minus. And you actually get to decompose the cohomology of your manifold according to the reducible representations of those Lie algebras by their Lie algebra action on forms. Okay? So this is the general theorem. Of course, what I'm doing in the previous slides is actually identifying which these irreducible representations are in the UN and the UN cross UN case. So this seems to have brought us a long way, but in fact it hasn't. So here I have our table from before with ticks and crosses, and now I actually put here reduced holonomy. And right now in the reduced holonomy, what we are getting is that the cohomology decomposes, but you don't get yet to say like you have identity of Laplacians. I don't have operators that I can meaningfully say that they have the same Laplacian as DH, for example. So if you just ask for reduced holonomy, you can't really say that you have identity of Laplacians, but you can say that harmonic forms decompose into the composition of forms. There's no Frobisher spectral sequence that you can consider there right now, and well, those questions are just maybe beyond crosses. So there is something about reduced holonomy, but in principle, what makes a difference between, say, Keller and G2 structures is that in the Keller case you have identity of Laplacians, and that's what allows you to say so much about Keller manifolds. And if you look at G2 structures, you actually know very little about their topology. So it's important to have identity of Laplacians. Let's say that seems to be a good thing. So that's what we get now. It really is important to have an Skt structure. That operator delta n, the one that goes up in the diagonal, it has a Laplacian, and the Laplacian is really the same one as the DH Laplacian. Okay? And the proof just uses two things. One is just integration by parts, as you know from school, and the other one is just the fact that the Hodge star is extremely well behaved for the UPQ decomposition, or for the WK decomposition of forms, just I to the P plus Q. Using those two things together, we get to compute that the adjoint of delta plus is just the complex conjugate with a sign. So taking adjoints and complex conjugates is essentially the same operation once you consider this decomposition of forms. So you get that here D plus was the bit that changed the duality, so it was the sum of delta plus and delta plus bar, so the ones that actually move out of the diagonal, those were the bits that changed the duality from self-dual to anti-self-dual for forms. And from this result here we see that delta plus bar is just minus delta and star. So you have the D plus squared, on the one hand is the Laplacian, and on the other hand is just the square of this thing here, which is just the Laplacian for delta n plus. It's a very simple proof, and just a matter of looking at the correct operators here. Another thing that you can prove is that in an Skt manifold, you should not consider the del cohomology, but actually the twisted del cohomology by del bar of the symplectic form. And for that one, the cohomology actually is isomorphic to the DH cohomology of your manifold. So the proof, I don't really have a proof written here. It's just the idea is that you consider an automorphism of forms. It's a natural one to be considered if you're coming from the generalized complex world. And if you use this automorphism of forms, it actually relates the del operator with the del bar plus operator, and this n operator with the wedging with this form. This thing has two implications, this little computation here. One of them is that, of course, if you look at del plus n, it gets sent to del plus this thing here, which is the other cohomology, so you get the isomorphism of cohomologies. Another thing that's actually quite important is that it has an implication for computability. Because right now I'm writing delta plus, delta minus, and you're looking at it and thinking, what the heck are these operators? And what this is saying is that after an isomorphism of the space of forms, it's just del. It's just the usual complex derivative. Okay? So these things are actually computable. It's not just a bunch of operators that I'm flashing in front of you, but you can actually just use standard complex techniques to say something about these things. And a corollary of this theorem is that you can decompose age as a sum of these two, the age as a sum of these two operators, and they satisfy the correct commuting relations. So they give you a spectral sequence, and now this spectral sequence is generated at the second page because the DH cohomology is already isomorphic to the cohomology of this guy here. So once these two are isomorphic, there's no further killing that happens beyond that point. So you actually get the generation of a spectral sequence early because of this identity of cohomologies and Laplacian identities. Okay, so good. I have 10 minutes or so. Okay, so that's where Hodge theory finishes. So these were the green crosses in my table. Now I'd like to talk about deformation, so that's going to be very quick and somewhat sketchy, but I hope it gives you the correct idea. So the idea is that we would like to deform these Skt structures, and the way to deform them, well, you can choose, there are different ways to describe a deformation. The ones that seem to be most suited for this setting is that you deform the whole t plus t star by an orthogonal transformation of t plus t star. So here we have, deform everything by an orthogonal transformation of t plus t star. The point is that Skt structures are defined by a bunch of linear conditions, and those would be preserved by orthogonal transformations. There are some conditions which are open, for example, a positivity of a metric, and those would also be preserved by this kind of thing. And all that you are left with is integrability. So this is a good way to deal with the problem. Of course, if you are doing just small deformations, that's really what I'm interested in, some sort of stability theorem. So if you're just going to do small deformations, you don't have to pick a generic element in the group. You can pick things in small elements in the Lie algebra and just exponentiate them. So the small deformations are just given by exponential of elements in section of spin. So this is a section of Wedge 2 of t plus t star. And the problem of what are the deformations of an Skt structure, that's not a good problem to treat. Or maybe it is, but it's not the one that I'm going to. And you might compare that with the problem of deformations of a Keller structure. If you have a Keller manifold and you have a function, you can always add dd bar of the function to the complex structure, to the symplectic structure, and that gives you a new Keller structure. So it's an infinite dimensional deformation problem, and let's say we don't like that so much. So we try to bring it down, and then the way that I'm bringing it down here is that I'll ask in terms of stability. So what I assume is that I have an Skt structure. I assume that this Skt structure was given a generalized complex extension. So I have an integrable generalized complex extension of an Skt structure. I'll deform the generalized complex structure and ask, when can I still deform it so that I still have an Skt structure hanging around? Okay? So this is the question. Which deformations of this generalized complex structure which extends my Skt structure can be completed so that I remain in the Skt world? Okay? Now, deformations of the generalized complex structure J1, they are given by exponential of elements in the Lie algebra, and you can actually get these elements to be of a specific type, like this one. When you write it this way, you actually have a unique, technically I should actually have put plus the bar and ask for real elements. It's a typo here. So you ask for real elements that underlie such elements here. And So these are deformation of J1, and once you do it like this, you have gauged away a few things. The idea is that every deformation of J1 is in one-to-one correspondence with one such element. Okay, so there are a lot of automorphisms of J1 which I'll use later. But the first thing that you do is just say, well, how can I describe the deformation of J1 alone? The deformation of J1 alone are given by one such element, and this is just the linear algebra part of it. And what I'll do is assume that this linear algebra part actually gives me an integrable deformation of J1. Okay. Now the whole process is actually done in a power series way. So what we do is expand this alpha, assume that this alpha is actually an analytic function, and write it in power series. And you start doing it in a term by term case. So you are led to consider like the linearization of this problem. So that's a common. Okay, let me just make a few comments here first. Integrability is always given by dh, and once you do this orthogonal transformation, you can just say I'll keep dh and change everything else. So you change the PQ decomposition, you change everything by this orthogonal transformation. Of course, we would much rather keep the UPQ decomposition and change the age. That seems to be a more reasonable thing to do. So that's what we do. We can twist back. So now instead of having the age as the one that gives me integrability, I have this twisted the age here. So it's twisted by this element alpha, and that's the one that's going to give me the integrability of the deformed structure. Now I'm actually in a good position because I can look everything at the original PQ decomposition. I don't have to flow the composition of forms anymore. I can just look at time zero for the composition of forms, and the price I'm paying is that I'm twisting my differential operator that gives me integrability. And if you look at something like this and you linearize, so this is like the first order term would be just really the commutator of dh and alpha. And of course there are more terms that you have to deal with, and if you want to see how it's dealt with, you just read the paper. But at least as far as linearization, that gives us a good idea of what's going on here. You just pick this, you are led to consider this kind of thing. So the graded commutator of dh and alpha. Now dh had that decomposition into delta plus, delta minus, and n. So you just define this graded commutator operator, so that's kind of what's acting on alpha here. And you have to check that these guys here actually do what you would like them to do. So they should look like Lie algebraic differentials. You have to check that they actually do what they do. And delta minus, for example, is not a Lie algebraic differential because it's associated to a non-integrable maximal isotropic subspace. But anyway, you get these operators here, and they assume that they do what they do. It takes a few pages to check that they actually do what you would like them to do. And for example, what does it mean to say that alpha is giving me an integrable deformation of J1? So this guy here, the UN0 determines J1. And if you look at the arrows that you should get once you twist by this operator dh alpha, you have alpha and you have delta minus, the commutator of this thing. So whenever you see two arrows, the way to compose them is really by taking the commutator. It's not just following one and then the other. But it gives you something here, and integrability of J1 means, for example, that the commutator of delta minus and alpha minus should be 0, that the commutator of alpha plus and delta plus bar should be 0. Now you look at the other one. The other one is the difficult one that where we actually get a condition. So this one I'm just assuming that's deformed within the integrable structure. So I'm assuming that these zeros are already there for me. And now I look at the other one. So this is the one, U0n is the one that determines the second structure. And here are the different components of alpha. So I have alpha minus coming down here, alpha plus here, and alpha plus minus goes to this space. It technically doesn't exist, but later on when you commute with dh, you have this n bar. And in fact the arrow that actually exists is the one that comes down here with n bar and then goes with alpha plus minus this way. But anyway, the commutator is a non-trivial operator, so it's I just keep that space there. So you see that just by having that alpha that uniquely described your deformation of J1, when you act on this space you get a bunch of things, and I would like to be an Skt structure, so I don't want to move the diagonal more than one down. So here's my diagonal, if I'm at U0n. I can move one down, so that's here, it's okay. This one is moving 2 down, and this one is actually moving 3 down. So I would like those to be 0. This one that moves 3 down, actually 0 already from the previous slides, the commutator of alpha plus and delta plus bar. It's this commutator here, alpha plus, delta plus bar. So that one was 0 just from integrability of J1, I don't have to worry about that one. This one here, I still have to worry about. It's not something that dies automatically, so if I just pick the unique alpha that gives me the deformation of J1 modulo some symmetries, gauge symmetries that I have taken out, then in principle I get something non-zero here. So this thing here, Unfortunately, in my slide this is red, which is to say that it's danger. But for you guys it's just black, which is just as dangerous as the other guys, which are not dangerous at all. Anyway, so this one is the dangerous one. And what you can do now is just pre-compose your deformation with something which preserves J1. So you can actually pre-compose your deformation with the automorphisms of J1 and see the effect that has on J2. So again, I'm giving the linearized picture, and this is the linearized picture. You get, these are the guys which preserve J1, so they correspond to maps that don't change the PQ, the P degree for J1. Here it is. And when you have such a guy, it gives you one extra map. So I'm commuting with the H, so it has a bunch of arrows everywhere, and the arrow that's relevant for us is this one here. So I can change that dangerous thing that's red in my slides and black for you by something that's green here. And as long as I can kill it with this green guy, I'm okay, I can deform. If I cannot kill it, I can't deform. So that's the obstruction. Okay, the obstruction here is going to be, so this is the equation that I need to solve. It's something about the graded commutator of alpha plus minus and n bar, and there shouldn't be a bar here, and the graded commutator of alpha plus and delta minus bar. So these operators here, these already denote the graded commutator. And the equation that I want to solve is del bar plus of beta is equal to that. Well, del bar plus square is 0. You can actually check that this thing here is del bar plus closed, and the question is just whether it's del bar plus exact. So that's the kind of standard thing you get in deformations. So what you're getting here is the deformation to deforming the Skt structure actually is a cohomology class. So this is the first one. I mean, explicit writing for you in terms of the components of alpha. You keep on getting more of them if you don't just do linearization, but actually consider all the terms of your Taylor expansion. And they always lie in this space. It's always the same question that keeps on coming. So we make some choices, and those choices lead to some new terms, and you have to keep on asking that those terms vanish. So the theorem that we have here is that the obstruction to deforming Skt structure lies in a del bar plus cohomology. I'm just giving here some indices that denotes that it lives in this particular spot here. Okay, so the del bar, the obstruction lies in this space, and if this space vanishes, then J1 can be completed to the formation of an Skt structure. If it doesn't vanish, well, then have some obstructions, and you have to deal with them. Okay, so that's essentially what the conceptual framework that explains what Salomon, Fino, and Parton were finding in their Skt paper. Now there are some interesting things that where you can forget about these obstructions. It's kind of a silly deformation, so you might say that I'm not saying anything smart here. I actually believe that might be the case, and yet I'll say it. So if your deformation parameter is actually a section of V minus, then what it's doing is this. So the Skt structure is here. It's a complex structure here. That's my Skt data. Now if alpha is something that's in V minus, what alpha is doing is just changing V minus. It doesn't change, doesn't touch that space. Okay, so I'm just changing the complex structure I'm choosing on V minus. If somehow I can do that and remain integrable, then brilliant. I didn't do anything to the Skt structure, it's still on V+. So I still have an Skt structure. So there is no obstructions there. Okay, it's actually some sort of trivial deformation. Seems a little silly. Maybe interesting is the fact that you can just use one of those. So if you have a Keller manifold and you deform the symplectic structure, well, it's known that the formation of the symplectic structure take you out of the Keller world, so you get something which you cannot really complete with a complex structure to be Keller anymore, but you can actually complete it to be Skt. So you can, in principle, once you deform the symplectic structure in an integrable setting, all you have is a Hermitian, generalized Hermitian structure. So if you have two components of the Nine-House Tensor, and what I'm saying here is that you can actually change I as a generalized complex structure so that one of those two components vanish. So you keep an Skt structure. Actually, it's a little bit better than just saying generalized Hermitian. And the point is that the crucial step of deforming the Keller structure. So if you are deforming a Keller structure by a 1-1 form that's small, you remain Keller and you don't have to worry about that. The problem is when you deform by a 2-0 form. And when you deform by 2-0 form, what you're doing is actually deforming just V minus. So you can just put that on V minus and V plus stays the same. So if you ask me what is this Skt structure, what would be the tree form, for example, so maybe I can give a better picture in terms of bihermitian So we start with Keller, in which the bi-Hermitian data is really I plus is equal to I minus, and you deform I minus. So you now really have two structures. One of them is I plus, which remains being the Keller structure. So don't deform I plus, and just deform I minus into something non-integrable. And that's what's going on there. They're making a deformation on V minus. So on V plus, you actually still have the Keller structure. So what's the tree form? The tree form actually is 0 right now. But you can phrase everything so that it looks a little bit better than just saying I have a generalized Hermitian structure. You can change I minus in a way so that it's actually a generalized complex extension of an Skt structure. So that's it.